In the name of Almighty God, I am Hassan Koshi, and today I want to talk about a mean field approach to multiple long delayed system, which was written by Giovanni Giacomelli and Antonio Politi from the University Institute of Pure and Applied Mathematics, Department of Physics in United Kingdom. The concept of multiple line delayed feedback system is introduced and discussed with reference to a paradigmatic model. We analyze how the resulting chaotic dynamics is affected by the delay distribution. Via a mean field approach, we show that a spatio-temporal representation equivalent to the one developed for the single delay can be extended to this wider class of dynamic systems. Numerical simulations are complemented by a theoretical study based on the multi-phase scale analysis, which in the vicinity of a Hopf bifurcation allows mapping the initial model onto a complex Ginzburg-Landau equation. As a result, we find that the only relevant feature influenced by the multiple delays is the size of the coherent spatiotemporal structures, which in turn depends exclusively on a generalized variance of the delay distribution. Lattice structures are widely studied in many fields such as graphene, carbon nanotubes, the Ising model, percolation theory, self-avoiding walks up to lattice QCD, and cellular automata in the case of the macroscopic lattice, such as optical networks. The propagation times are large with respect to the typical system time scale, suggesting the presence of a long delay regime in this letter. We introduced and discussed a broad framework where several line delayed feedbacks are simultaneously active, all with the same nominal lag as a paradigm of a real systems. The delay times fluctuate around an average value. We discuss a simple but general model and compare numerical simulations with a normal form obtained via a multi-scale analysis showing that the dynamics is essentially determined by the weight of the delay distribution. As a consequence, we show that the system is strongly resilient to perturbations of the microscopic parameters, for example, delay, times, and coupling. Now I want to go through the introduction. In real physical systems, finite propagation velocities always lead to delays in the transmission of information. This is a particularly relevant feature of the mammalian brain, where the delay is indeed due to the propagation time of action potential along the axons. In many cases, this effect strongly affects the overall dynamics, possibly increasing dynamical complexity of the stationary regime. Delayed interactions have been investigated in several physics contexts, from the control and stabilization of the asymptotic regime to the implementation of the reservoir computing protocol. A particularly relevant class of systems is that where the delay is much longer than the intrinsic timescales of the system without feedback. For review, you can see, for example, the reference 8. This setup naturally induces a multi-scale regime, which can be effectively described by introducing new independent variables, a pair of spatial and temporal coordinates. This parameterization goes well beyond the formal descriptions. It allows developing a mathematical formalism able to grasp and reframe the overall scenario. The most peculiar feature is the structure of the temporal autocorrelation, which sharp revivals, which evidence the presence of a multi-scale dynamic. They are located at multiples of t plus nu, where t is the delay and nu is almost equal to 1. It's typically a small correction. In such a case, the spatiotemporal representation can be carried out by decomposing the time variables as t is equal to sigma plus theta t, where sigma belongs to between the zero and the temperature. Is a pseudo-spatial variable. T plays the role of the system size, and theta is an integer pseudo-temporal variable. The temporal series can be accordingly reorganized as spatio-temporal patterns were otherwise hidden. Propagating structures characterized by drift nu become clearly visible. In some contexts, the field variables change very slightly from one to the next unit, allowing for the representation of the evolution rule via a partial differential equation where theta can be treated as a continuous variable. This happens, for instance, in the vicinity of a hop bifurcation, as truly discussed in reference 15. Another interesting example is laser dynamics, where the almost continually along the time axis is a consequence of the vicinity to a perfectly integrable limit. So far, most of the literature focused on systems characterized by single delay. An exception is that of neutral field, where distribution of delays are naturally included with the goal of, for example, identifying the relevant bifurcations, as in reference 17. On a more general level, multiple hierarchy long delayed systems have been considered in reference 18. Here we consider setup where multiple long similar delays are simultaneously present, showing that in a first approximation, the dynamics is qualitatively equivalent to that of an equivalent single delay model mean field description. More precisely, we find that the resulting stationary regime is determined by the dispersion of the delay quantified by a generalized variance, where the term generalized means that the quantity is determined by the averaging over positive as well as a negative coupling strength akin to the excitatory and inhibitory synapse present in the neuronal networks, which have been mentioned in reference 19 and 20. In section B, we present studies on numerical results to illustrate the dynamics for various distributions of feedback distributions and different points of view. In section C, we developed two theoretical approaches. So first, we perform a linear stability analysis of the stationary fixed point solution to show that at a leading order, the transition point is not affected by the presence of multiple delays. Then, by implementing a third order multiple scale perturbative analysis, we show that the dynamics of the delay system is equivalent to that of a complex Ginsburg-Landau or CGL equation, similar to the single delay model, but with the important difference that the diffusion coefficient depends also on the dispersion of the delays. Finally, open problems and possible generalization are discussed in section D. Now I want to go through the section B, the model and numerical results. We address the problem by studying a simple model, the multi-delay Stewart-Landau equations. The first equation shows x to t is equal to minus 6 minus 1 plus I beta, the absolute x to the power of 2 multiplied by x plus sigma lower boundary is j ijx t minus tj. The first two terms in the RHS account for the local dynamics, while the last one accounts for a feedback realized by a linear combination of processes with different delays TJ. It is convenient to express the feedback term by referring to a global coupling strength. Nu is equal to sigma Lagrange J ij, and introducing normalized weight Wj is equal to ij divided by sigma j ij. It's also convenient to write Tj is equal to T plus delta j, where T is equal to sigma j. Wj is equal to Tj denotes the average delay, and delta j is the deviation characterizing each single process with delta j is equal to 0. Altogether, the ensemble of delays is described by the distribution W delta, which is not necessarily positively defined, since the single feedbacks can in general be either positive or negative. It is only important to keep in mind that the non-trivial oscillations may emerge only when excitatory coupling prevails. This is implicit in the assumption that integral derivative delta W delta is equal to 1, since all average are weighted according to the coupling strength. They generally differ from the naive arithmetic mean. The model 1 is the simplest description of the dynamics of a Stewart-Landau oscillators, reference 21 and 22, on a macroscopic lattice 23 until 25. For example, systems where the propagation delays along the links are larger than the typical time scales of the single oscillator. As such, it represents a generalization of the single delay case. Consider reference 15. So long as the delay dispersion around T is small, we expect the overall scenario to be qualitative similar. In particular, we expect the Hopf bifurcation discussed in reference 15 to be still present in one with an associated emergence of long time scales close to the bifurcation point. Hence, we start performing some numerical simulations of one. For example, beta is equal to 3 and nu is equal to 1.03. For example, slightly above the threshold value and is equal to 1 found in the single delay case. We first assume a flat distribution of delays around a large T for different values of the delays dispersion as quantified by the variance m2 is equal to delta j to the power of 2. We observe in all the cases an irregular behavior with strong intensity oscillations. In order to make the analysis more quantitative, we study the normalized autocorrelation function of the field amplitude xt is equal to the square root x and x star. Also, CAS is equal to xt and xt minus s minus xt to the power of 2 divided by xt to the power of 2 xt to the power of 2, where the over bar denotes the time average. In figure 1, you see figure 1 illustrates autocorrelation function for n is equal to 1.303 using a uniform distributions of delay between the interval t minus l divided by 2 and t plus l divided by 2 for t is equal to 2048 and l is equal to 0, 2, 4, 6, 8, 10, mostly the even values. The values reported in the legend are the corresponding variance m2 is equal to l to the power of 2 divided by 12. Instead, zoom on initial part here, tapering is equal to t plus 1. So in figure 1, we present the results obtained from the numerical simulations. The autocorrelations display an initial fast decay, a signature of a chaotic regime, accompanied by sharp revivals at multiplies of tapering is equal to t plus 1. Such a behavior found for different choices of large t values is indeed analogous to what observed in a single delay case and suggests a possible equivalence with a standard long delay description. With reference to the average delay t, the correspondence is strange by looking at the opposition of the peaks, which is unaltered, unaltered in the presence of multiple delays. On the other hand, the inset of figure 1, where an enlargement of the first peak is plate shows that the width of the peak increases upon broadening the distribution of delay here quantified by M2, indicating a first effect of the feedback multiplicity. More detailed information can be obtained from the study of the spatiotemporal representations reported in Figure 2. The parent of the single delay case is plotted in the box Figure 2, Section B as a reference, while Figure 2, Section D refers to a flat distribution of the delays with M2 is equal to 1.33. It is seen that the dynamical regime is almost the same as for the single delay case, which was previously identified as an instance of chaotic dynamics within the Benjamin fire stable region. Reference 26-27 of the equivalent CGL model 28 and 29. The only apparent difference is the increase of the spatial scale of the coherent structures, a visual manifestation of the slower decay of the autocoloration visible in figure 1. In an effort to empirically identify those features of the weight distribution actually responsible for the asymptotic pattern emerging for given known value, we have performed simulations for the same variance but different distributions. W delta, the parent depicted in figure 2e, refers to a setup with just two delays with equal width such that M2 is equal to 1.33 as on panel D. They are quite similar to one another, suggesting that the variance is the only relevant parameter of the delay distribution. This inference is confirmed by the equal shape of the autocorrelation function. See later for quantitative analysis. A more stringent test of this empirical observation can be performed by studying its distribution such that M2 is equal to 0 as in the single delay case. This is indeed possible since Wm delta can be negative for some delta value. Although obviously integral dA delta W delta is equal to 1, by definition we have performed a test by using the quasi distribution. W delta is equal to 1 divided by q square root 2p exponential minus delta to the power of 2 divided by 2q to the power of 2 multiplied by 1 plus alpha multiplied by delta to the power of 2 divided by q to the power of 2 minus 1. Suitably normalized and with 0 mean, its variance is m2 is equal to q to the power of 2 multiplied by 1 plus 2 alpha and can be negative if alpha is sufficiently negative. The resulting pattern is reported in figure 2c for q is equal to 1 and alpha is equal to minus 0.5 so that m2 is equal to 0. As seen, we have a strong agreement with the single delay case figure 2b, and even the correlation functions overlap. For alpha is less than minus 0.5, m2 can even become negative. In order to test the behavior in one such case, we have reverted to the simple setup with two delays, choosing their values and strange such that the M2 is equal to minus 0.32. The resulting spatiotemporal representation is plotted in figure 2R. See the caption for the detail. Again, we find a pattern very similar to that for the single delay, but now the structures are shrinked. The autocorrelation peaks are indeed narrower here, keeping all the other features. Summarizing the numerical finding in the presence of the relativity narrow distribution of long delay feedbacks, a relatively narrow distribution of a long delayed feedbacks. The dynamic is very similar to that of a process characterized by single delay equal to the mean value. This is true also when the distribution is not trivial as seen above. However, besides the pattern, similarly, it has emerged that the size of the coherent structures depends on the shape of the distribution W delta. It can either increase or decrease. In the next section, we develop a theoretical approach which supports the numerical observation, providing a perturbative expression for the dependence of the size of the special structures on the weight distribution WM delta. Now I want to go to the section C, theory. We start by representing a linear stability analysis of the homogeneous solution x is equal to 0 to show that the transition point doesn't change with respect to the single delay case. Let UHE denotes the infinitesimal perturbation given the presence of two main timescales. We assume that UHE is equal to U0 e to the power of R0 plus IL divided by T to the power of T, where I0 is equal to lambda 0 plus I omega 0 and I1 is equal to lambda 1 plus I omega 1 are complex numbers describing the stability over the two different time scales of inserting ansatz into the linear version of equation 1. We obtain I0 is equal to minus 1 plus nu m e to the power of minus r0 t minus r1 multiplied by a to the power of minus r0 derivative, where we have neglected 1 divided by t terms. Self-consistency requires lambda 0 to be equal to 0. That is a standard property of the delay models with a single variable where all Lyapunov exponent scales as 1 divided by t. Additionally, in the large t limit, we are authorized to assume omega 0 t is almost equal to 2pn for integer n. So thank you so much for watching my tutorial video until the end. Today is the 13th of June 2026 and time is 1:37 in the morning. In my based on my time zone is 12 o'clock. Thank you so much for watching my tutorial video until the end. Also, you can download the proper related consumer physics simulation file from our github.com/master